A mathematical model of a black hole is not a black hole. A weather simulation is not weather. Okay? A computational process simulating the human mind is not the human mind. There's this gap. There's this gap between our abstractions, between our computations, between our math and physical realization. And it's fascinating.
Welcome back to Tim and Keith's philosophical steakhouse.
Exactly, our fireside chats. I think it's been almost a month since we did the one that, or maybe 5 weeks even, that did the one that led to the this like doom debate analysis, which led to me going on doom debates and whatever, right? So that was pretty funny.
Yeah, so it was your fault that I didn't get to bed until about 3 o'clock in the morning the other day because I wanted to watch the Dune debate. And I thought you did a very good job. I mean, obviously the comments were really positive. I think everyone went from hating Keith Duggar to thinking that Keith was intellectually honest and not such a bad guy after all. So no, I thought it was really good. And props to you, Liron. I'm very impressed with how you handled yourself. The whole situation was great. Unfortunately, I did get the impression that both of you left feeling that you'd won the debate. What do you think?
Well, so I actually wasn't in it to win that debate. It's more like I'm always, and nobody ever believes me, but my goal is always the pursuit of, knowledge, right? And or sharing and whatnot. So I think we made a lot of progress in the sense that he agrees, and hopefully most people agree now. There's a technical sense, like there's a very technical sense in which LLMs, and again, like you got to be careful about how you define that, and whatever. Not LLM systems, not O1, but I mean just an LLM, sort of a autoregressive fixed context window type thing. I think there's a sense in which people understand that's not Turing complete, like in this technical sense, right? There's still these open questions, or folks aren't as convinced as I am. Let's say they're not as convinced as I am that actually has practical consequences. Like I think you're in that same camp, right? Which is that, okay, fine, there's this technical point in which that's correct. However, practically speaking, LLMs can generate Python programs that you could run in a system if you wanted to. They do have like a very large context window, and so if they're trained right, they can do a lot of important things. And so I understand that that's still an open question, and I have more work to do to convince folks that there is a practical consequence. So that's fine.
Yeah.
I'm happy with that.
It's certainly true that if you look at the statistical distribution of programs on GitHub, it will have a power law distribution, which is to say most of the programs will be short, low in complexity. And you distinguished the Linux operating system as being a really complex program. And any complex program could be decomposed into lots of smaller programs. But we should also distinguish the difference between something like a Python program and a Turing machine program. Now, there's this famous programming language called brainfuck, and that actually describes the operation.
Are we allowed to say that on YouTube? I wonder.
I think as long as you don't use the F word within the first 7 seconds, then you don't get dinged for advertising.
Oh, okay. Okay. All right.
Yeah.
All right.
And because machine learning models don't really understand, they won't know that we used it legitimately.
I got you. Yeah. That's
anyway,
a good point. Yeah.
Yeah. We didn't use it in an offensive way, but no, there is a difference between something like a Python program and a Turing machine. So a Turing machine is this hypothetical physical machine that can, it's got a program, and of course the program is fixed, because when we talk about language models being able to accumulate information in their context, the analogy breaks a little bit with the Turing machine. In a Turing machine, it's a finite state automata and it's fixed, and then it can write to an infinite memory on both sides.
To a potentially, it's to an unbounded, potentially infinite memory, not an actually infinite memory, folks. Like nobody's saying that exists. Like, no, you're right.
Go on. Distinguish the difference between potentially infinite and infinite.
Well, so potentially infinite is a let's say a procedure that can keep going in principle for forever, but it may not ever. I mean, you may never get to the end, right? So, for example, time, like the flow of time in the universe, may or may not. It may be potentially infinite. Like the universe will just keep going on and on and on, but it will never reach the end, right? There will never be an actually infinite time span. And so that's the difference. Like, for example, if somebody were to tell you that they had a register in a computer that was arbitrary precision, then what that would mean is that this thing could, as necessary, expand to have more digits of precision. Whereas if they told you, no, I have a register that's actually infinite, that's a very different kind of thing. Like that's a thing that in a finite amount of time can do an infinite amount of work, right? Versus saying that this is something that over an infinite amount of time it can do an infinite amount of work. So that's really kind of the point is, do you, like, in a single time slice, do you have an actual infinity, sitting there? And we don't know how to
Yeah.
build that. Like, we don't know how to build an actually infinite, register, but we do know how to build things that we can keep adding to and adding to.
So I felt that one confusion coming from Liron was the difference between the neural network weights being a finite state automaton and the input being the finite state automaton. Would you agree with that?
Yeah, I mean, there's this really subtle distinction, because, as I've said so many times, and I hate saying it every time I say it because it doesn't do justice to Turing, and is that a Turing machine is just, it's nothing but a finite state automata with an unbounded read-write tape. And so you have to think of that unbounded read-write tape as like an extension, really, of its state space, right? Because it can go and modify it and read it again. So it's basically, it can grow its state space to as large as necessary to solve the problem. And that's why it can explore, an unbounded set of computations, set of states, like whatever, because it can keep expanding, right? And I think there's all, and it's become more apparent to me over these last months, right, debating this issue, is that there's always been almost like this kind of ambiguity or sort of unfortunate choice of language in computer science where they refer to machines as both a model for a physical thing that you can build, as well as a notional mathematical model that maps to that, as well as a class of algorithms, right? And so that leads to some confusion. And I actually hope to clear that up in the future, or to present it in a way that makes more sense. But again, I think people have agreed, okay, there's a technical sense in which this is right, but does it make any practical difference, right? And I would 100% admit I haven't communicated enough or clearly enough my view on why it practically matters. And I could be wrong. I don't as yet I have strong opinions about it, but at the same time, it's not as clear cut as, it's not as clear cut whether or not an LLM based system, an LLM plus some Turing machines plus some, hash table it can read write to or whatever, the capabilities of that system are much less clear,
Okay, but another source of confusion is, Liron asked you about the human brain, and he said it's a finite machine, and you said yes, you accepted that the brain is a finite state automaton, but it runs an algorithm which is a Turing machine
Right.
controller, so we can effectively expand
Correct.
our memory, maybe even internally, but let's just use the external version of that. So then you're getting into this kind of quite ambiguous zone where you're saying, in the class of in the class of finite state automaton algorithms, there are one kind which can expand its memory, and then there's another kind which can't. And you're saying the types of algorithms which are learnable on, let's say, a language model, a bog standard language model, are not the kinds that can expand their memory.
Yeah, and so here's this ambiguity I was talking about because in computer science, you would not call an algorithm. So if you have an algorithm which is a push down automata algorithm or a Turing complete algorithm, you would never call it a finite state automata algorithm, even though the controllers for all of those machines are a finite state automata, right? So it's this funny, it's this funny ambiguity where, like, yeah, at the end of the day, all these machines are a controller, which is a finite state automata, having access to, no memory in the case of a finite state automata, or a stack, or read write tape, or whatever, right? And so, yeah, there's an ambiguity there. And what I'm saying is, in the space of all algorithms, there are algorithms that utilize external memory, and there are those that don't. And that currently, when we train LLMs, they are trained in an environment where they don't have potentially infinite read-write memory. They oftentimes have
Okay.
potentially infinite write memory, like output, right? But not read-write memory.
Okay, I got that. So what you're trying to do is imagine there's a diagram and you have finite state automata and you have Turing machines. And you're saying that rather than partitioning the space of algorithms neatly between those, clearly we can take an example of a Turing machine algorithm, because a Turing machine has this code book, which is the finite state automata.
Mm-hmm.
And
Yep.
you're saying in the
The
context of a
transition
Turing
function.
machine,
Yep. Yep.
yep, in the context of a Turing machine, we call that algorithm a Turing machine algorithm. But all of the
Right.
algorithms that run on finite state automatas, so on basic language models, you call those a finite state automata.
Yeah. I mean, that's my claim, right? My claim is that they're the algorithms that we end up with when we train um, these machines where they're set up to run as finite state automata. We end up training finite state automata, algorithms, right? And I think, and as I've said, I think that there's more work I have to do there to convince people of that fact, right? Which is that it's not just that they're in construction finite state automata because they have these fixed windows, right? They have these fixed context windows. Um, but what I'm saying is that, in addition, in my opinion, the algorithms that we access when we train those things come from the space of finite state automata algorithms rather than from the state of push down automata, Turing machines, etc.
Okay,
And
but
that's
you are
kind of the
saying,
extra work I have to do, right?
okay, but to be clear, you're saying that the substrate, so a native language model, can, in principle, it's a similar thing to you against Schmidhuber was saying, in principle, an RNN can be trained to be a Turing machine, but you can't train it with stochastic gradient descent. And he wasn't just talking about the infinite precision thing. I think he was talking about some other examples for solving parity where they can be something more than what they are if they are trained with stochastic gradient descent. Because the thing that confuses me is, look at how ChatGPT is trained now. It's trained to do RAG natively. In fact, I interviewed Patrick Lewis. He's the guy who coined the term RAG, a deep expert in RAG. And he was telling me that's how they do it at Cohere. When they train their models, it goes into a special RAG mode, so it kind of tightens up because there's loads of things you need to optimize when you're training RAG. And they are training these models en masse to expand their memory, through an external store. So, and when I say expand their memory, let me be clear. These things are not expanding their physical memory, but they are bringing into their context things from the outside, and they are potentially putting things out of their context to the outside. Now, RAG is a special case because I think it's only bringing stuff in. It's typically not bringing stuff out, although there's no reason why it couldn't do that in principle. So I'm asking you the question, how do you know that training models in this way wouldn't allow them to get into that space of algorithms which you would call Turing complete?
Okay, so and I'm gonna kind of skip by because I know we don't want to get bogged down like in the whole debate. So I'll try to skip past some things and just say, look, there's a lot of work that needs to be done to kind of clean up the language here, So I'll just say this, which is, as far as I know, the way in which RAG is trained never has a closed loop. Like it doesn't both write data to the database and read data that it's written to the database. It may do a retrieval of some data, internet search or whatever, and kind of run through that, right? Autoregressively sort of just like pass through that as part of its context and build up some hidden state and like do something. But it doesn't close that loop. So it doesn't both read and write to the same unbounded store. But as I've said like so many times, if you alter your architecture to where you do have that, like you do have this closed loop of the ability to read and write to an unbounded store, then you have a Turing machine, and then you had the potential of training or finding algorithms, let's say, from that larger space of Turing machine algorithms. But as far as I know, like anybody who's attempted to train such systems fails. And I mean, because you run into like really basic problems. So for example, let's suppose I'm trying to train such a machine. All right, like I've set it up, it can read and write to a database, and I start running the algorithm. Now, in order to do training, right, I have to run it until it gives me an answer. And if I want it to be a Turing machine, I need to allow for it to run for some unbounded amount of time, some unknown amount of time, right? Like it has to generate a stop token. It has to say, I'm done now, here's the answer. Okay, so I go to train it. I start running the thing. And, I'm waiting and it doesn't stop. And I'm like, all right, it's, been 5 minutes here and it hasn't completed yet on this sample, this batch, right? Like, what do I do? Do I let it keep running? Or do I prematurely terminate it and throw that run out? What do I do? So this is the problem, is that Turing algorithms can run for an unknown amount of time. They may never halt. So you're immediately faced with a very difficult problem during training, right?
Yeah, I'm glad you said that. So the problem is during training. So you could,
yes,
the whole stopping token thing, that's an artifact of RLHF. So we teach them to stop. We teach them to prefer a certain verbosity and length and so on. Certainly when you just train language models just on the raw distribution of text, you can just run them forever. And they never say stop.
Well, I mean, in order for it, halting, stopping is a basic requirement for algorithms. So for a Turing machine to do what's called decide a problem, it has to halt and give an answer. It has to halt and either say yes or no, right? And so there are many mechanisms by which you can indicate that the computation is done. You can have special states that you enter, right? Like if I enter the halting state or halting state 6 or whatever, it doesn't matter. Like then I'm done. Or you can write some special thing to the tape. You can say like, here's the answer, or the answer is between A and B, open paren, close paren, whatever. But you got to have some way of indicating that the computation is done somehow. And here's the problem during training is exactly what I said. If it hasn't halted yet, what do I do?
Yeah, okay, but I think we're kind of conflating two things. So on the one hand, we could talk about today's language models that are trained on internet data, and we can hypothetically imagine that there's some kind of transfer between that manifold and the manifold of Turing machine programs. Another thing we might do is let's just throw it all away and start again, right? So why don't we create a massive data set of Turing machine algorithms? Some of them will halt and some of them will not. Now, I believe there's some interesting structure of Turing machine algorithms. It's fascinating to think about what that structure is. And what we might do is just heuristically run a whole bunch of those sampled programs, because we could build a generator, or maybe we can be a bit smarter about it. We can create these little units of Turing machine components that crop up all over the place, because I think that it's like Francois Chollet said with the kaleidoscope hypothesis, right? That there's all of these priors of the universe, and then they additively compose together to produce the kaleidoscope, and intelligence is reversing back from that kaleidoscope into the priors which went into it. there must be something similar in Turing space, and this is related to Chomsky's ideas about nativism and so on. There's probably like a nice set of primitives that could compose together in an interesting way, and we could generate a bunch of Turing machines based on those primitives, and some of them would halt and some of them wouldn't, and there'd be a very interesting structure there. And maybe we already run them, so we know if they halt or not, and we build a large language model on it, and we get this manifold of Turing machine programs. And then maybe we try and map that manifold to the manifold that already exists. But that, I think, would be an interesting thing to do.
I mean, I agree. It would be very interesting. And this falls into the category of what I've been saying for a long time, which is we don't yet know how to train from a very rich space of Turing complete algorithms. And so maybe the proposal you just made will be a pathway towards that, right? Maybe that's not even, maybe we don't even need to do that much human engineering. You know, maybe if somebody just finds some clever tricks, some improvements to SGD or some alternate, hybrids of that plus neural evolution or something like that, they'll find ways to search the space, right? And I totally believe that that's possible. I'm just saying empirically so far, and it's kind of an empirical question, empirically so far, people have failed. And it's a very fascinating and, interesting result. Like why? Why is it so hard? There may actually be some deeper truths there. And I don't know. It is a fascinating question.
The space of Turing machine programs, of course, is infinite, right? Or maybe you would say potentially infinite.
Yeah.
Countably infinite.
It's countably infinite. Yeah.
Yeah, because I guess the broader problem in AI is overcoming ambiguity and searching. Because it seems that we wouldn't need to sample all of those Turing machine programs to come up with some statistically salient algorithm. But maybe that's not the case. What do you think?
I think it's a big mystery. So, and here's where I may be like woefully out of date with computer science knowledge. So if I am, I apologize. And actually, if anybody out there can educate me on this, I would love to know more. Which is, as far as I know, the last time I looked into this, we know so very little about this space of algorithms, right? Of the Turing complete algorithms. We just don't know a lot about them. I think there's sort of a few facts that are known, like, most algorithms never halt or this type of thing. We know that it's countably infinite, that type of stuff. But I think in terms of the structure of the space of all algorithms, either a lot isn't known, or I'm not up to date on the lot that is known. But I think it's fascinating. I think there could be lots of interesting structure there, especially if like you say, you mentioned this language earlier, BF. I'm just going to call it the BF language. You folks can spell it out if they want to, and it's like the simplest kind of mapping from a Turing machine to a programming language. It's got like characters for move left, move right, write something, kind of open a block, close a block, and like that's about it. Not much more than that. And that's why it's called BF, because if you ever tried to write a program in it, you'd want to quit really soon and go find something else to do. But maybe, and of course we have our higher level languages, right? But the curious thing about the vast majority of programming languages that we've developed is that if you just generate strings in that space, most of them are not valid programs, right? Like you have to kind of follow some type of a grammar in order to generate valid programs. And even if you follow that grammar, the vast majority of programs are like probably pretty useless. They're like bugs, or they just like don't do anything, or they infinitely loop. What if somebody could come up with and I'd love if any work's being done on this, please let me know. But what if somebody could come up with a language where almost every single program you generate is a useful program of some kind?
Yeah.
That would be cool.
A couple of things
right?
on that. Do you remember when we spoke with Daniel Roberts from MIT? And Daniel, I'm sorry we haven't released your show yet. We will as soon as possible. Whenever there's a lag releasing a show, it's because of love and care on my part. It's because I want to do a good job of it. But he was talking about quantum field theory.
You are a bit of a perfectionist sometimes.
I am. It's the curse of perfectionism. But we're not going to do that on Keith and Duggar's philosophical steakhouse. We're just going to stick them out. But no, he was saying, in quantum field theory that they also have this ridiculous blow up of particle interactions and so on. And the way they reduce the complexity are these kind of heuristics like sparsity and locality and symmetry and whatnot. And, as you say, we could just enumerate all of the possible combinations of this space. Most of that wouldn't be valid Turing machine programs. But, also there are many, many abstractions on top to, write a generating function of useful Turing machine programs. But then I'm asking the question, well, we keep coming back to this on MLST, that there's no true Scotsman, that we need to go to the fundamental level of computation. Wolfram, talks about the Rouliad and these kind of graph cellular automatons. We're talking about Turing machine space, but we also are guilty of talking about the same kind of thing with agency. Or you need to have the low-level particle dynamics. You need to have the real ontological particles. There's no point having some higher abstraction. Because if you look at what Cholet is doing and folks advocating for discrete program search, they're kind of saying, well, forget about the Turing machines. Why don't we start with something that we believe to be fundamental? Mm. And those are Spelke's cognitive priors, this core knowledge. So if you start with the premise that there is core knowledge in the universe, maybe not the universe, but our minds. I'm not sure if that's a distinction which matters in this case. But if you start from some structure and you write a generating function over that structure, which is what Cholet advocates in the ARC challenge, would that be good enough?
I mean, this is there's so much. I have so much that's so appealing to me. That approach is so appealing, right? And I think this is pretty similar to what Walid Saba, tells us too, right? Which is that there are these universal templates, and if we've got enough of those, and if they're well specified enough, then you can have these grammars that generate super useful algorithms. So definitely, I think there's a lot of appeal there. I know that it's criticized a lot, and people, say, well, it hasn't worked, or this project failed, or that project failed. But I do kind of feel that those may be a very interesting path forward at some point. And actually, I think if I were to guess, where we'll end up some long time from now, like 50 years from now or more, is we'll have hybrid systems, right? So there'll be components that we've trained, constructed, generated, whatever it is, through those mechanisms. There'll be components that are handcrafted by humans, and then there will be machine learned components that we've learned how to put together in an interoperative way, right? That'll probably really be the future of artificial intelligence, if I had to guess. Like the pendulum will swing. Eventually, people will, it will kind of plateau in what we can do with stochastic gradient descent and ever larger, massive, training data centers, and then the sort of dream coder and program synthesis and ARC challenge and Spelke and template type approaches will start to produce more and more, and then we'll figure out we still need a little bit of human ingenuity to make sure they're all working together well. I'm a big fan of those approaches.
Yeah, and it gets back to the functionalism discussion. We'll touch back on this again when we talk about Searle, but there's always this notion of the universe is hideously inefficient. It's created these beautiful kind of recursive minds that we have, and we have all of the priors that help us understand the universe and how this happened. I mean, we can talk about the evolution of language and cognition and nativism and so on, but it's very, very mysterious. But we know it was a very kind of long drawn out, inefficient process, and evolution had a lot to do with it. But then there's the question of, okay, well, now maybe we could design something which does the same thing. Right, and that's kind of what functionalism is talking about. It's saying if we could design a system which performed the same abstract functions as the thing that we did, and it has the same behavior, then it might be isomorphic. Now, of course, someone like John Searle would say, well, there's an ontological difference. there's a difference in the causal structure. Even actually in functionalism, there's huge debates about what kinds of causal structures you need to maintain. Like Chalmers, for example, he says that, there are certain counterfactual trajectories and, you need to have a very rich causal structure in order to kind of create a good enough simulacrum of the real phenomenon. But the point is, though, that I think I believe this, that there are probably uncountably many other configurations of systems which would be as if intelligent. And it's kind of like the no true Scotsman argument to kind of say, well, that one's not really intelligent or that one is intelligent, when in fact, in basically every situation, they behave in the same way.
Yeah, and this is kind of what happened in our Discord, right? Because fresh off the episode that we did on whether or not O1 could reason, which led to all kinds of debate and abuse on YouTube, and and Liron's response and me going over there. In parallel to that, in our Discord, somehow, and I forget how it was, I forget what the origin was. We have to go back and trace it. We got into this huge, I don't want to call it a flame war, but this huge internal MLST Discord debate about John Searle and the Chinese room argument, because I mentioned the Chinese room argument, right? And one thing that happened like early on in that debate is people accusing / mischaracterizing Searle as saying that he denies that a machine can understand. And in fact, that's the total opposite of what he said. He's been saying this whole time, right, that the only thing that can understand are machines, right? And that we're a machine, and currently the only examples of things that can understand are biological machines, okay? But that doesn't mean you couldn't build a different kind of machine. Like, his only claim is that it has to be a machine. It has to have a realization. It has to have I think the correct term too is embodiment, right? Like, it has to have a physical realized embodiment, or not, maybe not. Let's just call it a realization. We'll get into embodiment later. And that realization has to have some sufficient causal structure, right? As you said, yep. Like an internal causal structure. He as far as I know, he doesn't exactly specify like what that internal causal structure is or should be or whatever. He's just saying that it has to be there. So you can't just have like an ethereal algorithm that's kind of running ethereally on some substrate that doesn't have that causal structure. You've got to have this realized causal structure. And I agree with that. And I also agree with you and Tim that there can be many different forms or many different substrates upon which we could build that causal structure. And maybe there's more than one causal structure. It's like, okay, this causal structure is sufficient for understanding. This alternative causal structure is sufficient for understanding. There may be a whole bunch, right? And there may be a whole bunch of different physical ways in which you can realize that causal structure, but it does have to be realized.
So John Searle is quite possibly the most misunderstood person or philosopher on the planet. I think the Chinese room argument is probably misunderstood by about 99% of people online. You've pointed out a few of the confusions. Some people say that he is saying only biology as a machine substrate can give rise to consciousness and therefore understanding. And he doesn't say that, as you said. He says it's the only existence proof. And I'm not a huge fan of the actual Chinese room argument itself. I think it was a product of the time. And he was talking about semantics. So the broader theme is he's talking about certain patterns of physical causation. And that's many theories of semantics are basically talking about certain patterns of physical causation. So there are things that happen in the world, and all of these chains of causation end up materializing, not materializing, but end up being in your mind, and those links form semantics and how you understand the world. And he's pointing out this Chinese room argument as an example of the deterioration or the, how those links can be broken. Now, our friend Jez in the Discord server, he said, well, Searle's argument is not a theory of semantics. So what's the purpose of this? It's not telling us anything about semantics. I want to learn about causal theories of semantics. And Searle is just giving an example of why he thinks this particular situation doesn't have semantics. And then I think he pointed to Nagel's bat, that wonderful essay from Thomas Nagel. And of course, that's not really a theory of consciousness either. That's a very similar thing. It's just talking about, in a particular inconceivable situation, how we wouldn't be able to understand what another conscious experience is, but it's not really talking about what consciousness is. The other thing that John Searle is misrepresented on is people call him a dualist. And he's not a dualist. Right. He's a physicalist. He thinks there's one ontological substrate, and maybe we'll get onto that in a minute. But it's I think he's misrepresented by a lot of people.
Yeah, I think I'd rank him up there right next to Chomsky in terms of being misunderstood and misrepresented. And you wonder sometimes about the sociological phenomenon that caused that to happen. But I think, and Jez, I love Jez. Having him in our Discord is a real, privilege for us because he's just a precise thinker and seems to know like some ungodly amount of philosophy knowledge. And I, on the one hand, I finally was able to see his point. I don't think it's fair. I see his point, which is his point's kind of like, okay, there's the Chinese room argument, but it has all these, problems, and it doesn't really provide a theory. And it's almost like he's saying it's a teaser, but and therefore it's not really worth that much because it's just a teaser for where the real work, needs to be done. But I think you have to understand that a lot of times, that philosophical article, and by the way, Tim and I are big fans of the Stanford Encyclopedia of Philosophy, right? And even it says, and many philosophers that let's say oppose maybe the resulting intuitions of the Chinese room argument admit that it's one of the most important arguments like ever made in philosophy, right? I think there was a joke where somebody, and I'd have to look up the reference, but it was hilarious, where he said, basically the field of cognitive science can be defined as the field which tries to prove the Chinese room argument false. So I mean,
yeah, it's an existential
it's had a huge
crisis,
impact. Yeah, and so I don't think it's fair to just ignore that. Like it's a very good argument because, or there's a sense in which it's a good argument because if you tell it to a person, it allows them to kind of immediately and intuitively grasp that there's a question we need to answer. Right? And a lot of times I've heard it said that philosophy is really one of the biggest tools we have for deciding what questions do we need to ask? Where are the unknowns? Like, where are the holes that we need to poke at? The threads that we need to pull, right? And so the Chinese room argument makes it viscerally clear that there's something we need to think about here. And actually, we should say what the Chinese room argument is. Do you mind? Because I'm sure we have a lot of listeners who may not know it. So I'll just be brief about it, which is, John Searle says, imagine there's this room, okay, and inside the room is a guy with a bunch of books and rule books and dictionaries and sort of all kinds of things, okay, that allow them to map sentences given to them in Chinese, okay, into answers or other sentences given in Chinese. So, for example, a Chinese person can walk up to this room and it's got a little squawk box or a little, thing that can slip a note under the door with some statement in Chinese or a question, and he'll do this procedure, this algorithmic procedure to produce a result, and he'll give it back. In this room, imagine that it's just, it passes the Turing test or whatever. Like people slip notes under there, they get them back, and they think that these are coming from, from a person who really understands Chinese. And his point is, it's obvious that this room doesn't understand Chinese. It's a guy who has no clue anything about Chinese. He's just performing this sort of mechanical algorithm. If somebody slips under the door or the crack there a joke, Okay, he's going to translate it into like, some answer like, ha ha ha, that's really funny. He's not going to be laughing at all. He's going to have no understanding that that was a joke, right? And so this argument
Yeah.
is immediately obvious to people, which is, yes, something's missing here. Something is missing in terms of understanding. And that setup, that Chinese room setup, has been used to explore many other, cognitive aspects like consciousness, intentionality, etc. Right? I mean,
Yeah.
I think it's a great argument for bringing about that intuition that there is a question that needs to be answered.
We'll get back to the decomposition of kind of cognitive functions in a bit, because that's very interesting. Because in the original paper, he was talking mostly about intentionality. But when you read his later work...
Understanding. The original paper was all about understanding. Yeah, yeah.
Oh, I think it was intentionality and understanding, if I remember correctly.
Okay,
but we can go back and have a look in a minute.
But, yeah.
But my point is that you can swap those words out for things like agency and consciousness. Certainly, there's a wonderful talk which we'll reference now on the screen, which is John Searle talking at Google about maybe 12 or 15 years ago. And I do recommend that you folks at home watch that talk if you actually want to understand what John Searle is talking about, because he's super duper clear in it. And one thing that struck me in that talk actually is very, very instructive. He said he knew that his dog was conscious, not because of its behavior, but because of its mechanism. It had eyes and it had a mouth, right? And it was a mechanism much like his mechanism. And of course, the broader point of Searle is that it's physical mechanisms which give rise to patterns of physical causation, which give rise to our consciousness. Because to Keith's point a minute ago, the reason why Searle in the room didn't understand was because there's this phenomenal, which is to say there's this conscious experience, possibly of laughter. And if you break that causal patterning, so if the conscious component is not there, then of course you wouldn't have the complete understanding. Therefore, you wouldn't understand. So it's very interesting to kind of distinguish this kind of function and behavior from the mechanism, because when we spoke with Murray Shanahan, he said, well, I can feel if something is conscious if I share a physical environment with them and the behavior is kind of intelligible in a certain way, then I might intuit that thing has consciousness. And of course, this is quite slippery, because then you could start talking about a large language model as if it had consciousness based on its behavior. So Professor J. Mark Bishop, he wrote a very interesting, I think he was the editor of a review piece on the Chinese room argument. So he's been studying the Chinese room argument for about 30 years. And we had him on the show a few times. And I must admit, I think the first time I had him on the show, I didn't fully grasp this thing, because I think this is a thing that takes years of kind of reflection to actually understand. And certainly, I think by the second or third time I had him on the show, I was starting to grok what he was talking about. But his opening line, I think, on the second or third time he came on was this. He said, "Indeed, it's my belief that computation cannot realize understanding, deep mathematical insight or consciousness, and hence that there exists a gap, a humanity gap between that which can be achieved by computational processes alone and that which can be achieved by humans, potentially using computational tools. 3 a priori philosophical arguments, John Searle's Chinese room, Lucas Penrose's argument, and his own minor contribution to the debate, the dancing with Pixies reductio, and we'll talk about that in a second, underpin this claim. He said that if any of these arguments hold, then an unbridgeable ontological gap between computation and mind is firmly established. Well, aside from a diet of too much dodgy sci-fi, he said he believed a deep confusion between epistemic concerns, for example, how we as humans might establish if a sister or brother had understood our words or was feeling pleasure or pain, etc., and ontological, for example, how we might actually instantiate consciousness, pleasure or pain in a machine, lie at the root of this widespread quasi-religious belief that computation can actually realize cognition. He suggested that any commitment to what the American philosopher John Searle famously termed strong AI, the view that suitably programmed computers can actually understand natural language or genuinely instantiate any other mental capabilities of the humans whose behavior they mimic is quasi-religious. And he went on to talk about, computational processes can never make us milk or produce energy from sunlight or, sadly, make us rich. So,
yeah,
beautiful stuff, eh?
And I agree with you, by the way, that I think the first time we spoke to Professor J. Mark Bishop, maybe I wasn't prepared either to really fully ingest what he had to say. So it's nice to go back and read it with a new lens and understand things better. I think and this is a problem with the language too, because Searle, and I know this is going to sound weird. I know this is going to sound really weird to us as like computer people, okay? But he distinguishes between compute and machine. All right. So when he's talking about a computer, what he's talking about is a kind of machine that doesn't have that sufficient causal structure, okay, to produce understanding or consciousness or whatever, okay? He is absolutely not saying that there isn't a machine that we could build from some non-biological stuff that could have that causal structure. In fact, like J. Mark Bishop's statement is maybe even slightly stronger, because he is really focusing there on the human, right? And saying, and you could almost read into that we'll never be able to produce that in some non-human, machine. I think we're definitely far away from being able to do that. But Searle is saying, no, we can build a machine that can do that. It just has to have this necessary causal structure. It has to have this realization with this necessary causal structure. And both Searle and I think even almost kind of, let's say more beautifully there, J. Mark Bishop are getting at something which is really fascinating to me, which is, on the one hand, we have these beautiful equations and abstractions which do really well at mapping to and explaining and predicting stuff that happens in the physical world, right? This is the remarkable effectiveness, or the unreasonable effectiveness of mathematics, if you will. And yet, on the other hand, we know in principle and in fact that these abstractions and equations do not capture the whole story. A mathematical model of a black hole is not a black hole. A weather simulation is not weather, okay? A computational process simulating the human mind is not the human mind. There's this gap. There's this gap between our abstractions, between our computations, between our math and physical realization. And it's fascinating. And I think this is where it's really largely unknown, and there's so much work to do there to better understand that. But I think you have to accept that there's this gap. I mean, the arguments for that are just too strong.
Yes. So the two major components and by the way, I agree with you that Bishop probably is actually taking a stronger position than Searle did. But we'll come back to Bishop in a second. But yeah, so Searle is saying that we need to have physical realization in order to maintain the fidelity.
With a necessary causal structure. Yeah.
Precisely that. So the core of it is there needs to be a necessary causal structure, and he's saying, I believe that some kind of physical realization is necessary for that. There's another component to his discussion which has led to accusations of him being a dualist. And that is basically this, that he thinks that the correct physical instantiation and therefore the correct physical causal structure gives rise to consciousness. And he's a materialist, so he only thinks there's one physical substrate. But he makes the case that this consciousness is subjective. Now, of course, we can refer back to Murray Shanahan's view on this. This is capital S subjective, but not in a dualistic way. So it simply means that you as an observer, you do not have privileged access to what is in my consciousness. And that's part of the reason why he thinks that when we kind of simulate cognitive processes in machines, because they wouldn't have access to this special subjective experience, they would not have the full fidelity of understanding. Now, I don't think Searle explicitly said this, but I think he's basically making the argument that our consciousness strongly emerges from a certain physical instantiation and causal structure. Maybe you can explain what that means.
Yeah, and this is a super controversial topic here. Strong emergence. Is there such a thing? Does it exist? So I'll put my cards on the table and say that I believe that both weak emergence and strong emergence are real phenomenons. So let's talk about what those mean. So in general, what emergent means is that if you have a bunch of parts, okay, like a bunch of molecules, for example, and let's suppose these molecules follow, laws, like the laws of statistical mechanics, for example, and you put them together, that it's possible for the whole, the sum of enough parts to exhibit behavior, dynamics, if you will, that are just fundamentally different from what the individual parts do. And strong emergence would say it's possible for them to exhibit behavior that is not even derivable from the behavior of the parts. Okay? Now, like modern physicists, I don't know what, I haven't done a survey, so I don't know, but if you talk to most of them, they're really strongly, or the ones who are vocal, let's say online, are very strongly reductionist in the sense that they're like, nope, the standard model, all I need is a standard model and I'll be able to compute everything and derive everything. Except they really can't. They can't do it in any remotely practical sense whatsoever. Okay, like the poor quantum mechanics guys, they can't even really compute past helium. When they try to go beyond too many particles, they just get totally slammed by computational problems. And they'll come in and say, yeah, okay, fine. None of my computers can do it. But in principle, I could. And the fact is, even in principle, all the theories we have, all the effective theories I've ever seen, they at least have points where they break down. Okay, they have singularities that crop up when you try to apply the integrations or the effective theories. And as soon as you have a singularity, what comes out the other side is undefined. So in my view, I think it's true that there are both computational barriers as well as in principle analytical barriers that we cannot cross. We can't get from this side of parts to that side of the emergent behavior, right? I think that this is possible, at least. So if you take something like, a good example is, fluid mechanics, like the behaviors of vortices and waves and the giant, red spot on Jupiter and things like that. And then you keep going up and up to life itself, life as an emergent phenomenon, or gliders and the game of life, these type of, little things that stay stable and move around. And it's like what Friston talks about, things that have these Markov boundaries and these sort of stable dynamic attractors that form a thing, that can kind of persist over time. All those things are definitely weakly emergent. Some of them may even be strongly emergent. And a lot of people who are even opposed to strong emergence in general, when faced with consciousness, maybe accept that, okay, fine, that's the only strongly emergent behavior. I think Chalmers said this to us, right? He said, yeah, I'm not really sure about all these other emergences, but consciousness may be the only example of a strongly emergent behavior.
Yes. Quite an interesting analogy with Searle. I mean, of course, they have a completely different ontology. I mean, Chalmers has an information ontology. I mean, the weird thing about Searle is he's actually quite no nonsense. I mean, if you actually take the time to understand what the hell he's talking about, it's surprisingly no nonsense. And you said something very interesting there, which I think we should save for our agency discussion. But I believe that agency is also physically realized. And there's a distinct difference between the type of agency we have in the real world and simulated, but maybe we can save that. But the other thing you said, though, is there are many boundaries of subjectivity. And this is very important for building AI systems. Wolfram is hinting at it when he talks about how we are computationally limited as observers. This argument from Searle is another great example of that. And this is all just pointing to how it might not be possible in principle to simulate many things in a computer. I wanted to touch on Bishop's Dancing with Pixies Reductio before we move on. So that was his main contribution.
Well, can I just,
so,
I just want,
go on.
Can I jump in with two? Yeah. Can I just jump in with two things? So, in preparation, or actually not in preparation for this, but as a result of that debate in our Discord, I watched that Google talk, Searle's Google talk, which I hadn't watched before. And I agree with you. There's this element of no nonsense pragmatism to him, because I didn't know the story he told at the beginning, where how he got down this whole rabbit hole in the first place is, I guess he was maybe leading a research program at some point long ago, and he kind of walked over to the let's say the cognitive science team or whatever. And he's like, hey guys, what's up with this consciousness thing? How come you guys haven't solved this problem already? Right. And they're like, yeah, no. We're not really working on that because it's not science. And that kind of set him off on this path. Like, wait a second, why isn't this science? Like, what are you talking about? And I wanted to also comment on Stephen Wolfram. And what's the phrase he uses? It's computationally bound, right? Isn't that the terminology?
His observer
so
theory.
Sort of computationally limited computation. I think it's such a cool framing of it. It's really interesting, saying how anytime, obviously, let's suppose for the sake of argument that, certainly the universe is manifesting a computation. It's unfolding as a computation. I even think it's a hypercomputation. But let's suppose it's not a hypercomputation. Let's just say it's some Planck scale or sub-Planck scale, pixel simulation, like whatever. The point is, it's this, you can't even fathom how complex that computation is. It's obviously so many orders of magnitude, I'm not even sure, higher than the computation that's happening in your brain. And it's fascinating to me, this point that Wolfram makes, that so many of the things that the abstractions we create, the laws that we find, the science that we do, the behavior that we observe is due to this fact that we have this much less computation than the phenomenon that's unfolding, before us. It's like they're compression artifacts. Like in the sense, all our scientific theories are compression artifacts. To me, it's just fascinating, and that's why I'm always excited to see what he puts out. Though every time Stephen Wolfram publishes something, like some article or blog post, by the time I get to the end of it, because it's really massive, I get to the end and I'm reminded of like how little I've accomplished compared to him. Like, how does he produce all this stuff? I don't know.
Yeah, that reminds me, there's a really good article by Stephen Wolfram on recursion. And for the last third of the article, he's citing Gödel-Escherbach and Hofstadter. And I think there was actually a formulation of this in Gödel-Escherbach, like a simple recursive function, and studying how it could give rise to these structures. It's actually kind of similar in principle to how a cellular automaton works. And then Wolfram did a whole load of different examples of this, and he kind of saw there's this branching factor, and sometimes you get cycles back, and sometimes you get these amazingly beautiful patterns, and then they weirdly stop for no apparent reason. And there's this whole space of computation, which is fascinating. I don't want to spoil the surprise on that, because Wolfram is actually going to come on and we're going to discuss that with him. But it also has echoes of our fascination with recursivity and the recursive mind. I think there's a lot to be said for that. Mm-hmm. And also, Keith, what do you think about this concept of computational subjectivity, given that we are Turing machines? If you think we are Turing machines, then why in principle would there be computational subjectivity?
Well, at the moment, I have a very simplistic view on that. And again, for anybody listening, you should always take my simplistic views as potentially just ignorance, right? Like maybe I haven't thought deeply enough about something, and so I've reduced it I've done the reduction thing that I sometimes rail against. I've reduced it to something simple for now. It's almost like a placeholder for me. It's like, okay, I got this simple thing for now. Maybe I'll dive into it later. Okay, so for me at the moment, I kind of agree with at least what I think is a fair representation of something Carl Friston has said in a blog post or somewhere, which is that let's suppose you're let's suppose you're a machine. Okay, let's suppose you're a machine and you're running a computation. All right, and you start off without any sensors or any data whatsoever on the computation you're performing itself. Like you don't know how much memory you're consuming or what the temperature of your CPU is or whether or not a particular loop has been running for a long time. Like you just don't have any kind of telemetry on your own computation. If you start hooking that up, okay, like you start having data and knowledge about yourself and the computation that you are performing right now, right? Then when you get to a certain, what Friston calls temporal and counterfactual depth, okay, once you have data from your own internal activity, processing, causation that spans enough time, okay, both in the past and the future, like your ability to kind of forecast out what you're going to do. And once you have enough counterfactual depth, once you're able to think about alternate paths that you could have done in the past, that's once you get far enough along that depth, you become self-aware, you gain, consciousness, and maybe some other, cognitive aspects.
Yeah, we should probably save some of this for our agency discussion, but we did have a bit of a slightly different interpretation on that, I remember, because I felt that he was talking about the depth of nesting of the Markov blankets, which give rise to a kind of counterfactual depth of planning. So his thing is that you are more of an agent when it's as if you are planning more steps into the future, so your planning horizon increases. And when that happens,
could we ask him? Could we? Because
maybe we
are
could
so
ask
fortunate
him.
to have. Yeah, I mean, we're so fortunate to have him as a friend and a contact. We should maybe email him, see if we can record like 5-10 minutes of him explaining this to us. That would be amazing.
Yes. But even that, I guess, is a form, if you think of it computationally, is some form of recursivity. But he's saying that there's some kind of Goldilocks
zone
of depth.
Yeah. Well, I mean, the depth. So the depth can be nested. So, I mean, I see what you're saying so I don't know if he thinks the nesting is a necessary component. But certainly it could be nested. If you have enough depth and I guess in some sense too, it almost has to be because since your mind, one of the most efficient ways in which you can do depth of computation is recursion, and so it probably is nested. But it would be really interesting to get his take on that and the degree to which he thinks nesting is a necessary component versus just an optional or sufficient component.
We need to get Friston back on. I think what we need to do, Keith, is I want you here. We need to get you in a room with Friston.
In the UK. Oh, I would love to meet him.
We've got to. The thing is, I mean, maybe I can just go and film at his place, and we can do it over the internet or something. But I would love for us all just to be in a room, sipping a sherry, as you say, and discussing the meaning of the universe. True. Yes. So, but anyway, we'll save that for our agency discussion. But there was one objection from CogChamp on our Discord, I seem to recall, and this was quite an interesting objection. He was saying, "Yeah, we need the physical causal structure," and he was saying it's like an oxymoron to say that computers don't have causal structure. So, we have all of these algorithms. I mean, there are books written about this, like that the algorithms are affecting us in many ways. So they are somewhat, maybe not agential, but they do have causal power on us. So if there is a space of causal power on us, why could we not shape that space with the right algorithm?
Well, I think maybe they're CogChamp and Searle and possibly us were talking past each other. Because Searle is saying it has to have a certain causal structure, not just that any old causal structure will do the job, right? And so, sure, computers, a computer is a kind of machine. It does have a causal structure. When it's performing a computation, there's obviously a causal structure there. Otherwise, the computation wouldn't work, right? Like, the transistor charges cause this, the clock cycle causes that. I mean, so there's a causal structure. I think what Searle's saying is that you have to have the right kind of causal structure. There's a particular causal structure. And he doesn't specify this, by the way. And this is kind of the weak point, or as far as I know, he doesn't specify this. This was the weak point that Jeremy and CogChamp, Jez and CogChamp point out, right? Which is like, okay, there's a causal structure there. Like, why isn't, or he hasn't told us what the causal structure is. Totally fair. I mean, it's Searle's claim that there's a certain kind of causal structure. And so I think it would be highly unlikely, highly improbable that the causal structure that we build into a computer, into a digital computer for purposes of, carrying out a calculation, I find it like pretty astronomical that would just happen to also coincide to the causal structure necessary for understanding, intentionality, consciousness, etc. And this is part of what is brought out in the Chinese room argument. Like, people intuitively know that a bunch of gears that you're sitting there like just churning to punch out like, the next conclusion to the sentence, like intuitively we think it's missing something. That's the whole point, right? It's missing the right causal structure.
Okay, so I think a fair interpretation then is Searle isn't completely ruling it out. He thinks that there is something quite special about physical, real mechanisms, right? And that is likely to give this rich causal graph that couldn't, that's not likely to be replicated with any algorithm on the internet or anything like that. Because it does bring us to the next adjacent point, which is there are, linguists like Stephen Piantadosi, and Stephen's written many papers saying that Chomsky was wrong and that language models do learn semantics. And he's got this theory which is called concept role semantics. And Jez is very interested in this. And, essentially it's saying that there is some kind of causal structure, but it doesn't actually need to be as physically materialized as we think. And there are internalist and externalist versions of this, because there's always the problem with having an externalist causal semantics, which is to say, well, I can imagine abstract concepts. I can imagine unicorns. I can imagine things that don't necessarily have any analog in the real world. And of course, you could go the next step and you can say, well, maybe they are composed of primitives which do exist in the causal world. But there is a whole school of thought that, in a computer, if we just represent this causal semantics graph to high enough fidelity, then the understanding threshold will be met.
Honestly, at this moment, I'm not prepared to rule that out. Like, I don't know that I can say that's not possible for understanding. Okay, for understanding. Yeah, I can't rule that out at this moment. I think, there has to be a certain causal structure. Whether or not we can get to that causal structure by virtue of just a special kind of program, like a complex enough kind of program, could be possible. And then if it even goes as far as to consciousness, well, then we're in a interesting situation, right? Because it's like, okay, I've got this computation now, which has somehow met all the causal criteria for consciousness, and I suspend the calculation, and so it's just sitting there stored, on a disk drive now. There's a bunch of like bits represent. Maybe I even gzip it, so I've gzipped this file. Like, that file definitely no longer retains the causal structure, right? Because it's been compressed and it's not running, right? But I can rehydrate it as now a conscious, conscious being. So that'll definitely open up a bunch of interesting territory. I mean, I think clearly, definitely Bishop, I think, is arguing against this possibility, if I understand him, correctly. I think Searle too, probably thinks this is not not the case, right? I don't know. I think
Okay.
that's a tough one.
Another thing is, I don't think Searle explicitly has a position on internalism or externalism, but I think people assume that he's an internalist because he talks about the brain. I think he believes that
Right.
the brain alone, so you have the brain in a vat, and because of the special physical mechanism in the brain, that
Yeah.
brain would be conscious, which means there'd be some subjective component. But based on what he said in the Google talk, I think he is I guess this would be technically embodiment, but there are many different brands of, or flavors of externalism, which are pointing to there being cognizing elements outside of the brain and maybe the body and so on. He said that his dog has eyes and a mouth, and that contributed to this mechanism of it being a conscious being. So I think it's reasonable to assume that he's at least open to the idea of there being like an external component to cognition.
Yeah, I mean, yeah, that would be an interesting question as well. I think my reading of it, and this is just my reading of it, is that he does require a certain internal causal structure. Like without that internal causal structure, you're not going to have consciousness or understanding. And then, like you said, I think maybe he doesn't require externalities, external, causation, but that there can be a part of it, and or they can be a part of our ability to know or to infer that something has consciousness. But for example, I would bet, just from having read a lot of them and looked at his videos and whatnot, that if you were to put the question to him, does a person, let's suppose a person isn't necessarily in a coma, but they're somehow totally shut off from the outside world, but their brain activity is still normal. It's like a dream type of state, right? I think he would still argue that person understands whatever language they learned natively, that they're even conscious, that despite the fact that they currently have no external connections really whatsoever.
So J. Mark Bishop, his contribution was this dancing with pixies reductio. And this, I'm just reading a summary of it here, but it's a critique of computational theories of consciousness that builds on Hilary Putnam's ideas. So the key points are: 1, it targets claims that a suitably programmed computer can instantiate general phenomenal consciousness or qualia purely in virtue of executing a program. 2, it argues that for any computational system claimed to have phenomenal states due to its program execution, we can map those computational states onto state transitions in any open physical system, like a simple counting machine or even a rock. And 3, this mapping can be done for a specific execution trace of the program with defined inputs over a finite time interval. 4, therefore, if the original computational system has phenomenal experiences due to its computational states, then so must the mapped physical system, which leads to an absurd, he says, form of panpsychism, where consciousness would be ubiquitous in the physical system, little pixies dancing everywhere. The argument aims to show that computational or functional organization alone is not sufficient for phenomenal consciousness. Now, is it such a reductio ad absurdum to say that if we map a computational process to an open physical system, then the open physical system would be consciousness, and that's an absurd thing? Do you find that absurd?
So I mean, like Putnam's rock is sort of the original version of this, and yeah, I think it is absurd to say that a rock is conscious, but I think so. There's a couple little loopholes,
well,
or
not the rock, the overall organization. Would that be conscious?
Well, but this is specifically about, I mean, the rock, or in the case of Dancing with Pixies, an open system, right?
Well, so he's saying take a cognitive process in your brain
Mm-hmm.
and represent that as a series of like hose pipes and water and paper cups and whatnot. Just map it to some open physical system so it's performing the same computation. And then let's imagine that thing in the physical world that we've just mapped it to is also conscious. Does that seem absurd to you?
Well, I just want to clarify here. You can do that same mapping to a rock. That was the whole point of, Putnam's rock, is that you could even map it to forget about, nice pipes and hoses and gears and things that, maybe are cool. Like you can even just map it to like the sort of atomic dynamics of a sufficiently large rock, right? To some subset of its dynamics. And yeah, I think that's absurd. Like it's absurd to think that the rock has consciousness, and I think it's like somewhat absurd to think too as well that a bunch of gears and like whatever of an arbitrary structure that we mapped it to necessarily have consciousness, right?
We are Fristonians, right? We're Fristonians. So Friston says that there exists certain dynamics and functional organization which give rise to consciousness. So if we say yes to that, then why do we say no to mapping a cognitive process to an open physical system?
Well, I mean, so I'll tell you why. Like, I'll tell you where kind of the problem boundaries are in that argument, which is that one thing I really like about the dances with pixies reductio ad absurdum is that it does lay out very precisely the argument, and in fact lays it out so precisely that its own weak points are explicitly put in there. Okay, which is, it says, if we pay careful attention to it, that for any finite period of time you can do this mapping. Okay, so like you can choose some finite amount of time, a day, a year, or like a whatever, right? In principle, you can do this mapping. Here's the problem: is that in whatever thing you choose and you do this mapping, suppose it's an hour, okay? An hour plus epsilon, okay, an hour plus 1 second. Those two systems will have diverged unless they have exactly the same causal structure. And this is kind of the key of what, Searle's pointing out, is like, sure, I can take, let's boil it down to like the absolute vacuum state of this problem, which is a Boltzmann brain in a vacuum and a large Putnam rock in a vacuum. Okay. And so if we all say, yeah, the Boltzmann brain has consciousness, it's conscious, it understands, it's, whatever else. Okay. And then there's the Putnam rock in a vacuum over here. And if the Putnam rock's large enough, I can map all the dynamics of the Boltzmann brain for any finite period of time to some subset of dynamics in the rock. Aha, the rock is, conscious. No, because outside of that domain, epsilon time beyond that, they diverge. Okay, so the computations are not the same. The dynamics are not the same. The causal structure is not the same, and that's the whole core of Searle's argument, right? And it's the sword that cuts through this idea that like just the observable functional behavior is enough. Like you have to have the causal structure built into the realization. But yeah, I think it is absurd to think the rock is conscious.
Yeah, I mean, I was just going to say that. Yeah, I intuitively agree that it is a reductio ad absurdum, because you could just take a trace of a cognitive system, and then it would diverge at epsilon 1 or like 0.0001. Yep. And then there are all of these intellectual exercises of the fidelity of maintaining the causal structure. So what if we have Chalmers did this with the combinatorial state automata, so we model the counterfactuals and we model some underlying process, and eventually maybe there'd be some threshold level where we would capture the phenomenon, and that's very interesting philosophical territory. But certainly if you just capture a trace, then of course it wouldn't be the same thing.
Yeah, I mean, I agree. I think it's fascinating. It's interesting. I think these are very deep questions. I think and that was the power of the Chinese room argument, is that it at least laid out this in question in a very visceral way. You hear the problem and you're like, yeah, there's something we need to think about here. And so it's definitely helped to spawn a great amount of research. All fascinating questions. I wonder how many we'll see answered in our lifetime.
Yeah.
I don't know.
Final thought. What do you think about Hinton winning the Nobel Prize?
Look,
Drawing for breath
think,
after I asked that question.
yeah, because I don't think I'm qualified to have an opinion, honestly. I don't really think I'm qualified to have an opinion because I don't know, I haven't surveyed enough the whole literature and everybody's contributions to it and whatever. So I just don't think I'm qualified actually to have an opinion. I did see a lot of, let's say, some of the controversy around that, and the one thing I do know is true is that academia is plagued by politics. Okay, it's plagued by politics and corruption and pettiness and gatekeeping and power struggles and turf fights and bad behavior and people not citing when they should and stealing work. I mean, so it's absolutely the case that academia has a lot of problems. Okay, whether or not any of those are relevant at all for this choice of Nobel, I couldn't say. I can't say. And so therefore, like, I take the award at face value, which is congratulations to them. I mean, they've obviously had huge contributions to the field of machine learning, and I would love to see any of the folks that we talked to on the show or interacted with, these kind of, like, let's say the godfathers of AI. I think they're all massively deserving of accolades. So that's all I can honestly
can't
say
disagree with
about
that. His contributions are undeniable. But
Yeah.
As for the credit assignment thing, no need to comment on that because we're going to release part 2 of Jürgen Schmidhuber, and he was pretty scathing, actually. So you can only imagine what he said. So I won't comment. I'll just let you folks wait until we release that. But the other controversy was, it was a Nobel Prize for physics. And this is kind of related to the whole Chomsky comments about, well, language models aren't a theory of, they're not a scientific theory. They don't tell you about what the thing is and what it isn't. And to what extent is deep learning, like, what has it got to do with physics, if anything?
So again, I don't feel that I'm qualified to decide what should and shouldn't count as a physics Nobel Prize. I certainly know. So we interviewed Daniel Roberts and Sho Yaida, right? And they have this beautiful book that I really liked a lot, The Principles of Deep Learning Theory, which in that case, it's the reverse. They're applying physics, ideas to the study of deep learning. And it struck me as totally legitimate, useful, something we should do more of. So I can't say it's impossible that machine learning work can't actually be physics or considered physics or contributing to physics. I don't think I'm qualified for this. These are way above my pay grade to decide what is and isn't counted as physics, honestly.
Yeah, but do you accept the analogy to Chomsky's comments on language models, which is that deep learning models are not a scientific theory in the sense that they don't provide a powerful explanation?
Well, but Chomsky was talking about, a specific. I mean, what Chomsky was saying is that if you use all these techniques, deep learning or whatever, and then you train a language model, it doesn't tell you anything about language. It may tell you something about physics, though, like because the physics was in the training process, was in the math, was in the engineering and the science that went into the process that trained it. So it's not like Hinton went and trained a large physics model, right? Like a large quantum mechanics model, and then he got the award for physics. It was more that the award came for the work that went into the techniques and the math and the science behind creating these models and training them.
Yeah, but the naysayers have said that the techniques that go into deep learning from a physics point of view are quite, I don't want to say trivial, but they're not that complicated. And indeed, people, physicists have applied their knowledge to deep learning. But does deep learning give us knowledge about how the universe works? Because I think that's what the whole pursuit of physics is about.
Well, on that particular score, like that question, like I'd have to say, not in my opinion right now. I mean, I'm not aware of any, fantastic insights that, uh, I guess the only one I can think of is I think there's something very interesting about the fact that hyper over parameterized models are able to generalize it all, and that they don't just overfit into absurdity, right? I think that's really interesting, and maybe that says something deep about, I don't know, the structure of, maybe that helps us explain the unreasonable effectiveness of mathematics, for example. But again, I don't
Yeah.
feel qualified to I don't feel qualified to comment on this specific award. I think
Yeah,
there are
that's
too few Nobel prizes to go around. Every year there are many more people deserving of a Nobel Prize than there are Nobel Prizes to give out. And so very difficult decisions have to be made. And I just don't feel qualified to
yeah.
second guess them.
Another couple of angles, and yeah, I mean, like we should just both say that we're allowed to have opinions even if we're not an authority on every opinion. But another comment was made that Nobel Prizes are given out almost speculatively based on the potential of a discovery. Because, of course, Demis Hassabis and a couple of guys got the Nobel Prize for I think it was the drug discovery thing. And this is certainly something which has huge potential. But the naysayers are saying that this is kind of validating a lot of the bad things. I mean, apparently Google in a lawsuit, even this week, have started citing the Nobel Prize. They say one of our VPs and top scientists, he just
Oh,
got the Nobel Prize. So what are you talking about that there's copyright problems? And I think Hinton is also starting to kind of double down and say, well, look, I told you so. In 10 years' time, these things are going to be doing everything. And that anything you think that humans are needed for now, they're going to be doing it. And it's lending credence to this idea that there's just no end in sight for this technology. And let me
right.
say as well that we all agree that this technology is revolutionary. It's changing the world. It's changing everything. People just disagree on how that is. Some people think it might recursively self-improve and its capabilities will just keep going up and it's really intelligent. And other people just worry about the social impacts of it and it reducing our agency and exacerbating inequality and so on and so forth. But no one's going to deny that this is a real revolutionary technology.
Yeah, and the stuff you mentioned, I'll come back to that. But what you mentioned earlier, like I said, there's politics aplenty, and in academia, and I cannot say in this specific instance that politics and corruption and other bad behavior played a role. Okay, but it certainly exists in academia. As I've said before, that's part of the reason why I'm not in academia, because I really had a very difficult, unfortunately, like I'm kind of genetically a Boy Scout or something, and I just had difficulty dealing with corruption that was wasting public money. Okay, like public money grants and things like that. So I'm out of there, right? I mean, so yeah, I can totally believe that it's being abused, certainly by corporations to get more money and power. Absolutely. As for like the disagreements about AI, yeah, you and I, we know that these are powerful technologies. A lot of what we talk about though is that, one, there are limitations to these technologies, and we're suggesting ways in which they can be expanded and further improved. And powerful tools can be misused. And I was happy, and earlier I didn't thank Liron too. I would like to, because it was a great opportunity to go on Doom debates, and I thought the feedback was tremendously positive. We got a lot of positive feedback. Funny enough, it seems like it helped to humanize Duggar, so I'm not quite as evil evil as I used to be. But one concept that we came up with in that podcast is that we should be talking about a lot more. We should be talking about a lot more AI harm. okay, which is the
Yep.
harm that AI does. It brings lots of great benefits. It's also bringing harm, and it's being misused to cause harm. And we have to think about that, and we have to wrestle that, and we have to reduce the harm that we accrue from AI and increase the good.
I agree with that. I mean, we didn't speak much more about Liron's podcast, but at the beginning, I was surprised that you said your PDoom was 25%. And
Yeah.
I've always listened to the Sam Harris podcast, and there are lots of folks out there who are really interested in existential risk, not necessarily AI, but pandemics and nuclear war and stuff like that. It's very legitimate. I mean, Noam Chomsky talks
Yeah.
about it all the time. He always says we're, like one tick away from doomsday, talking about the threat of nuclear Armageddon. This is all absolutely true, and I guess maybe I should be worried. I accept it to be a truth. It's just not something that I'm personally, that preoccupied with. So that's undeniable. And then there's the sort of the intermediate thing of harm from AI, non-existential harm, but just social harm. I'm completely on board with that. And then if you go all the way down that line, you get to this existential harm from AI. And for me, that would require AI to be agential. And for many of the reasons we've spoken about today, I don't believe that could happen even in, well, maybe I'll say in practice just to be safe for now, but certainly not something that we should be worrying about anytime soon.
Well, the nice thing from my perspective is if we could just get people to really take seriously AI harm, okay? Just take it seriously and look into it and try to mitigate it and try to prevent it, try to reduce it. A lot of the steps, a lot of the policy steps that we would take to reduce AI harm would actually reduce AI risk as well. And if we started to take AI risk seriously, it would reduce the chance of AI doom. So these are like steps in the right direction. And the reason why I want to frame it in terms of, or reframe it in terms of AI harm, is that's something that you could get, I don't know, like the vast majority of people, like 90+%, to resonate with. Like, yeah, I mean, absolutely. AI harm is it's reducing quality of life by leading to unemployment or people losing their jobs or no longer being able to get paid for the work they want to do. It's causing massive harm to our children, through like the social dilemma type stuff. It's sucking up attention into like completely pointless exercises like infinite scroll of content with no mental nutritive value whatsoever. I mean, if we could just get people to, almost all of them would resonate with some aspect of AI harm, and then we could start to take it seriously for policy, for public policy.
The thing that I don't like is the conflation of AI safety and AI ethics. I'm trying to find the paper that Penny shared the other day. Here we go. Yeah, there was a paper that I read by Dagmar Monnet called Deconstructing the AI Myth, Fallacies and Harms of Algorithmification. And we'll put a link to that on the screen. And one thing that struck me actually is, and I think it's fair to say that Dagmar is on the left, a lot of discussion is around the reduction of our agency as a function of AI. And many different philosophers talk about this. When I interviewed Luciano Floridi, he was talking about re-ontologization as we migrate to an information ontology. So we're basically living our lives in the infosphere and our digital identity is in the infosphere and we need technology to survive and so on. And perhaps that's more of a consciousness argument, but there are all of these arguments that are talking about various different components of our cognition, be it our agency or consciousness or whatever it is. They're being eroded as we acquiesce to technology. And, so that's I see that as a bit of a leftist argument, but I'm completely on board with that. That really makes sense to me.
Well, I mean, I think there are so many dimensions of AI harm as well as AI good, that the whole point is we need to be having these conversations. And now a lot of times the conversations become really like quite nutty. So I don't resonate with any philosophy whatsoever that doesn't correspond to physical reality. Okay, so like I start with physical reality as kind of my bedrock, and I think that no matter how much we don't like truths, we have to accept them as truths and then deal with them, head on. Okay, so but I think the nuttiness in conversations would kind of get worn down if there was a more robust conversation. So we need more people having the conversation. We need more voices involved, not fewer. We need real data, real science, real consideration. We can't leave the steering of AI to just the fringes of people. We need to find a way to talk about it with everybody.
I agree with that. And I feel that Luciano Floridi in principle is saying that. He's saying as we become increasingly divorced from the physical reality, even from a legal perspective, the territorial reality, these systems abstract so many of the physical boundaries that define how our legal system works, how we live our lives and so on. But I did want to comment on this point.
I wasn't trying to say I wasn't trying to say he was nutty. That's what I'm trying to say.
Oh no! I know what you were saying.
Voices. Yeah.
I know. I'm getting on to the nutty voices you were talking about. So this is why I don't like the conflation of AI risk and ethics. And you kind of pointed out why on your Liron discussion when you started talking about orthogonality and instrumental convergence, right? So there are all of these philosophical thought experiments which are used as justification for AI risk. And I think that they are extremely speculative, right? It's fascinating philosophy. I think it's legitimate philosophy, but I don't think they mix particularly well. Certainly if you want to be doing policy, I don't think that those arguments should be factoring in any way the same level of valence as talking about the other stuff we're talking about, like the effects of social media and bias and fairness and re-ontologization and all of this kind of stuff. I don't want to use the word science fiction, but I think it's completely on the speculative side of things.
Well, I mean, I completely agree with you there, which is that, and I agree with every point that you said. So yes, there is a whole host of speculative, things. It's really fascinating. Definitely philosophers and maybe, chumps like us should be talking about it, okay, and should be engaging with it, okay, 100%. And you're absolutely right. It's not what should be factoring into the policy, but what I'm trying to get across to folks who are concerned about AI harm, AI risk, AI doom, is you don't need science fiction and diamond nanobots and like whatever else in order to convince vast majorities of people to do things that you would like to have done that would help with those concerns, right? There's always this conflict. People think that public policy should just be run by science. They believe in kind of like a technocracy, okay? And that's not how the world works, and it's actually contrary to a lot of economic principles and political principles and whatever else. You've got to find, because you're dealing with this massive evolutionary algorithm, which is the 8 billion people plus every other life form on Earth in an ecosystem. And what you have to do if you want to steer that ecosystem in the directions that you want is you have to be able to find arguments that resonate with large fractions of the population, okay? And so you need to focus on the core and the simpler arguments that will resonate with more people. Let's do that. And if we do that, we'll be able to get better policies that not only will reduce harm, help to mitigate risk, they'll make us more prosperous, healthier, happier, overall have more resources to figure out how to solve the alignment problems, et cetera, et cetera. So, we've got to focus on human flourishing, I guess, at the end of the day, which I know, Sam Harris would agree with, right? Like if we focus on human flourishing and reducing harm, we'll get a lot of the policies we need to handle these other concerns.
Easier said than done. On that note, Dr. Duggar, we will round off this philosophical steakhouse episode. Let us know at home, folks, if you like this kind of thing. Me and Keith just rambling makes an interesting change.
Steakhouse, right? I love it.
Yes. Anyway, cheers.
Cheers.